Hello, my name is Klaus Christensen. I'm the leading advisor for dynamic risers in Statoil, and I'm here to give a presentation on the integrity management and operational experience of flexible risers we have in Statoil. Be a tough act to follow. It's been some very, very good presentations so far. But I'll try and see. I will give a short introduction to the historical development of flexible risers in Statoil. Jan has touched briefly upon it. I'll go a bit more into detail. Give some general observations regarding the flexibles we have, and then based on the latest experiences we have, present what we have found, more specifically on Caucus issues and generally the failure investigations we have performed, how we do our integrity management, the portals and the new developments, and the recommendations we would have in Statoil. So in 1996 we installed the first flexibles, 5 static pipes at the Gullfaks platform. The first dynamic risers were on Veslefrikk, 4 high pressure mud and cement pipes. I think they're actually still rating pretty high on the ID to pressure list. Then in 1992, we tied back the Snorre TLP with the static risers, and then, as Jan said, in 1995 to 2000, we kind of really took and embraced the technology and developed the high pressure, high temperature flexible pipe in order to develop the North Sea with floating production units. What is, I think, generally called the elephants. So that brings us to now that we in total have 20 floating production and storage offloading units, approximately 250 dynamic unbonded flexible risers, and about 500 kilometers of unbonded flexible flow line. On top of that, we have 10 loading systems with large diameter bonded flexible pipe, and all of it is being operated within 100 to approximately 380 meters of water depth. And all in all, the flexible riser technology has been vital for Statoil's oil production and been what can be considered a hugely successful product. But we also recognize the challenges there is with the technology. And what are the challenges? Well, the North Sea, as you all know, and as has been shown on the videos, is rough environmentals, and it's not the occasional hurricane, it's every week all winter. The 100-year condition, I think this is at the Øster Hansted, is a 33-meter wave. The storm, the 1 year occurrence is about 75% of the 100-year level, so every year they will expose to significant loading. We have cold seabed temperatures, and we do quite often step into the hydrate regime. So what do the Statoil risers look like? This is the pressure diameter plot. Showing, I think this is actually the original Vison riser, and we see that during the development of the Åsgard and the Norne fields and the Kristins, we developed the risers technology for high pressure and large bore diameters. Again, this has been used before, but as it's seen, they are all around here, and they are still, even though they were designed and manufactured 10-15 years ago, they are still on the cutting edge of what is being done with the product. I think the Vison riser is up here, and the scarves are here. Mind you, the scarf production riser is a serious pipe as well. What have we seen in operations? Well, we do see high dynamics, we do see high pressure, we do see high temperature, and we do see frequent fluctuations occurring at the same time. So it is, as Jan said, this is the worst case scenario for a flexible pipe to be operated in. We have seen that in order to meet the technology requirements the projects had at the time, we had to develop new polymers and new steel materials, new armor profiles to meet the high pressures, and generally the cross-sectional build-up. And that was done in the projects, which again has led to some challenging task of bringing it into operations. And do sufficient experience sharing in order to be able to operate them safely. Also, there has been a change in perception of the product from something you put out there into something that you actually need to look after. What have we seen? Yes, we have seen failures. That is clear, that it can be read in the paper. What we see is that we have only had small hydrocarbon releases, but we cannot rule out when we do our dissections that they could have been larger. We see that we can have them occurring at a very, very short time from the damage occurring to the pipe until it's been operating for several years until the leaks start occurring. We see that there will probably be some correlation between the cross-sectional buildup and the expected leakage rates. And we see and would agree with the BP strategy that inspections, monitoring and testing is vital in order to discover this early. And furthermore, we need to do the feedback from our damage investigations and feed that into the operations and into the governing documentations in order to ensure the continuous improvements. So generally, we try to recover and establish the root cause for all incidents we have. And one of the layers that has experienced a lot of incidents is the Caucus layer. I think the general assumption in Caucus design is a free and flexible structure that is not exposed to any significant loading. It's generally designed for collapse and for the crushing loads. That is not correct. The Caucus is exposed to other kinds of loading. Jan summarizes very well. It does see actual forces. It will see it either through the hydrate plugs or as we have with these multi-layer structures, where we see that I will present in more detail on the following slides. We see that they do have collapse modes that was not predicted originally, mostly due to the pressure buildup, believed to be under control with the work performed in the early 90s and early 2000 and mid 2000, where first it was taken out. They weren't used for gas injection anymore, since single phase seemed to be a problem with the pressure buildup between the second and the third layer. And then we found out that we could also have pressure buildup between the first and the second layer. Try to control it by the decompression rate, believed to be under control, but the latest findings we have on Muscat indicate that it's probably a bit more complex than that. So there's still significant work ongoing in understanding the collapse mechanism for the multi-layer structure. But I agree with you, Krasimir. It's something completely different than what is stated in the API, and it's not what's covered by the 0.85. The hydrate plugs is true. We have seen rip-outs of Caucus. I can only have been from hydrate plugs. The pull-out I'll present in the next one. We have been spared for the fatigue so far, we think. Caucus pull-out was presented at the OMEA. We first detected it in April 2011, occurring with 2 incidents occurring within a very brief period of time on Wiesen and Njord respectively. When we inspected, we found this. It's not an ideal situation for a flexible pipe. It's not supposed to look like that. The Caucus had spun out and was hanging free into the internals of the riser. When we did further inspections on the platform, we found this, which is very, very clearly an early stage of a Caucus tearing, and indicates very, very clearly that you do have actual loading occurring in the Caucus. That kicked off significant work internally in Statoil in order to understand this failure mode, and from now we have spent more than 12,000 hours internally, and we have had assistance from DNV for subsea and from the manufacturers. What is it that characterizes the multi-layer structure? It is that you have the sacrificial sheet, the pressure sheet, and the anti-creep sheet. And this one here is not sealed, so you will get a pressure buildup between this layer when you operate the pipe normally. That means that you will, to some extent, lose friction between the layers. Furthermore, with the Kevlar polymer, which has a high level of plasticizer, you will lose plasticizer over the period of time, and you will get a reduction in volume, which will increase the gaps you have here, which again brings you to a situation where you suddenly lose your interlayer friction, which is a completely basic assumption for the flexible pipe. It's not very well understood, but it's believed that friction will make sure that the loads is carried to whatever layer needs to handle it. When that assumption goes, it's very difficult to predict the behavior of the pipe. Furthermore, due to the creep of the polymer, you will stretch the individual windings in the Caucus, and you will start to transfer the gravity load in the Caucus. So it's not no longer a free and flexible structure. It's actually a structure that is transferring actual loads. So how did we handle this? So just to sum up, what we found after all the work, the major contributions was we had an actual load from cooling of the pipe, where the polymer would contract. We had a load from losing friction along the length of the pipe, so it would carry the gravity of the pipe, and we did have a load from pressure compacting of the polymer that the bulk modulus changes. The majority of the major loads are from cooling of the polymers and from gravity. So how did we handle this internally? We specify that in order to operate Koflon risers safely, you have to perform internal inspection. You have to measure the pitch of the carcass, and by doing that, you can determine the load level. You will have to establish the operational parameters, evaluate the pipe based on the models developed in the work, and you will have to compare that to the structural capacity of the carcass and see what is the utilization under conservative design assumptions. And based on that, you will decide what we need to do. Is it okay? Can we keep operating it? Do we need to have monitoring for the carcass to see if it's in place, or do we need to replace the pipe? So far, we specified that you must have continuous monitoring in order to operate multi-layer Koflon risers safely with respect to carcass tearing. That has also meant that we have replaced a fairly large number of risers and has given us a possibility to obtain learnings from risers that has been in operation. In April 2011, when we started the Koflon task force, we had 64 Koflon risers in operation. Now we have 24, I think. 22, depends. The replacement campaign is pretty efficient, as Subsea 7 probably will say later. So we decided that now we had a unique opportunity to learn. So the licenses agreed to fund a detailed investigations of all the risers we got in, and I think we have contributed to a significant amount of the meters Jan quoted he had examined. And we did full-length internal inspection. We did external sheet. We looked at the Analyst environment. We looked at carcass and armor corrosion in general, and at polymer aging. Further, it was split in two. So we did an initial investigation as we were respooling the pipes, and then as we found details that was interesting, we shipped them off for more detailed investigation. We also found out that we actually had to develop a complete independent database to handle all the data we received. So what have we seen? We have seen that the Analyst environment is a source of surprises. We see less condensation of water than we probably would have expected. We do see oil in some of the risers, quite often high seas. We see gas pockets occurring at the high points, which would be expected. We do see that the ones we have filled with liquid, they are actually filled when we take them in. That is good. So I think the general conclusion is that we do not fully understand carcass. The pipe Analyst. We see that we need improved and better models for diffusion and condensation. We most probably need to improve the end feeding sealing system. There shouldn't be all these high seas, and most probable cause is a micro leak across, and we need to improve the vent systems. We do see external sheet damages occurring more frequently than we would have liked to. We do see less corrosion near the damaged areas than we would have expected. We do see, though, however, for large damages, with ample access of oxygen, we see high corrosion rates. We have tested this, and we have seen that we can get very high corrosion rates, up to 1 millimeter per year. And additional testing have revealed that we do not fully understand the relation between CO2, oxygen, and temperature when it relates to corrosion, and significant work needs to be done to that. So far, it suggests that you need to have a reasonably large amount of oxygen available. However, with increased temperatures, that amount of oxygen reduces, or the amount of oxygen required to obtain corrosion reduces. So that can explain some of the observations we have with high corrosion on inner layers, but not on outer layers. But work is ongoing on that. And then we now see that outer sheeting aging models needs improvement, but you have made the advertising for the API tier 2, and we can only do the same. How do we keep track of our flexible pipes? We try and follow very closely what the BP has presented. I think we're getting to the point where a best practice is beginning to establish ourselves. So we do run the visual inspections internally and externally. We do the subsea ROV annually. We monitor for marine growth. We follow the CP systems. We see that they sometimes disappear faster than we would have expected. CP is difficult, so keep track and replace is the philosophy. We do the Analyst testing we have to do in order to detect the volumes, and we have Analyst vent gas systems on a number of risers. And again, we do the bore fluid and the Analyst gas compositions and compare those to each other. Then we have temperature and pressure readings and polymer columns. Coupons follow these and do regular follow-up on the risers. What have we learned the last couple of years, and what did we have to learn? Well, part of the incident with the collapses and the Caucus tearing means that we have had to learn to do long-distance internal ROV survey. This one here is, I think, at 680 meters into a Osgard riser, where they a bit further down had a collapse. This is hydrates forming, overshooting from the with gas overshooting from the commissioning peak. We have learned to detail carcass pitch and diameter measurements. We have learned to have a acoustic emission system for detecting for carcass failure. We have developed a internal system, which is here, based on ultrasonic sound. And we have had riser motion sensors lowered into some of the risers. That is not the Koflon issue. That is a clashing issue. And we have become very, very good at doing cost-efficient internal video inspection on risers, so you don't have to reel it from one reel to the other, but can just do it on the reel. I think it's 4 hours it takes now to do a full internal inspection of a recovered risers. But I think one of the challenges in riser integrity management is not obtaining the data. I think you can get all the data you want. I think it's what do you do with the data that's interesting, and that's the challenge. In Statoil, we have developed the riser integrity management portal, which allow us to, based on the existing systems, pull all the information we have on our risers and access them centrally. That has been necessary for us, since we have a large number of risers. It's perhaps not the best solution for everybody, but it seems to be working for us. That allows us to have a more or less online overview of all our risers and the condition, and they are all operating with a red, yellow, blue, green, I think the color normally is, green traffic light color system to see what is the condition of the risers. And it allows for very easy access, and also to find the old or the original design documentation, and all the inspection reports are accessible. So to sum it all up, what do we need to do? We need to keep feeding back the experiences we get and feed them into design. We need to improve the internal specs, and to, when we have the sessions, feed that into the ISO and APIs. We have a challenge that we design the pipes, we put them out there, and the first thing you do once you put an oil field into operation is to start planning how do you modify it in order to increase the oil recovery. So you have to be good at continuous maintenance and modification, and keep track of what are the changes you're imposing, and what do they do to your flexible risers. The non-singing riser is a typical example of that, where we didn't do that well enough. We also see that with a challenge like the flip system, it's so dependent on the topside monitoring. So each time you do a modification topside, you change the reflection coefficients, and thereby you potentially change the singing regime. And it's quite a challenge to keep track of a topside contract and remind them that they have to start doing analysis for subsea equipment. We see that the original design life of 15 to 20 years is being challenged. Now we want life extensions up to 40 years. We see that the design basis is being updated regularly. But we also see that with these 40 years, we do need improved inspection technology. I completely agree with Krasimir there. We do need reliable systems for data acquisition and condition monitoring, but we do need better systems to allow for the data feedback loop, to actually use the data. And we need to have efficient experience transfer between all of us. That is the operators, that is the manufacturers, and that is the integrity management contractors as well. And we do need to have the network meetings internally and externally, both with operations and with projects. So this is, I think, basically one of the key messages you had, Trond, in your risk level report. From design point, we need a better carcass. It has to be stronger. We have to understand it. And we have to actually manufacture the carcass we design. We do need hydrate detection technology. It's very difficult once you get a hydrate in a system to determine where it has been. You need to be able to say if it has been in the pipe or not. We need to improve the external sheet robustness. We see a huge challenge in operating risers above 95 degrees with bend stiffness in air. We do not believe we have 20 years service life. And we also, and thereby also indicating we need better polymer aging prediction models. And then my own personal favorite, we need condition monitoring of static pipes. It's a black box we have down there.
Thank you, Klaus. Thank you. Any questions from the audience? It's crystal clear. No. Krasi?
Lunch.
Krasi Doan of ExxonMobil. Klaus, you have mentioned that inspection and monitoring is vital for early detection of anomalies. I would like to pose the question, can't we just simply, get a better design of flexible pipe, kind of over-design, to address all of these needs? Or do you see a case where, regardless of what design is, you ought to inspect or monitor?
I think the majority of the failures we have seen have not been designed for.
But now that you understand,
so I think it's the unknown unknowns that's the challenge. I think the things we know, we put into the codes, we design for those. I think it's all the things that we as Henk Keisterlein says, there's so much about flexible pipe we do not know. So robustness will help to some extent, but I think it's so complex to operate an oil field and so many things happening that we do need to do proper inspection management or do proper integrity management in my opinion.
So is it the policy of Statoil right now to implement monitoring and inspection all the time for every single riser? Or
We try to do it. We also see it pose a significant challenge on aging installations to post-install things. We can get it into the risers as we're replacing them, but it's a modification project offshore typically takes 2 years. So the time lag we have from technology we put in until it's actually fully functioning as an integrity management thing is very challenging. I think you will probably find the same. So we try, but again, it's a priority. It's aging structures. Flexible risers are not the only thing out there aging.
Thank you.
Thank you, Klaus, for a good presentation. This is Christian Boe from Technip Norway. Can we expect to see 40-year design life on our next specs from Statoil? And if so, do you have any ideas on sort of what additional design checks or what we need to do to achieve that?
We're discussing that.
Thank you.
I think currently we are saying 25, but I think we actually have wrote 40 for Mariner. But again, I think we have to change a little so we get more into the integrity management way, because I think they can operate for 40 years. No doubt about it. But again, it has to be in the right conditions and you have to have designed it properly.
Can I just add that we are working, as you know, with life extension, and the problem with life extension is if you don't have data, coming back to that a little bit in my presentation, is that if you don't have it,
But
you cannot say anything about the condition.
No, that's what I mean. That was the change in regime. We've gone from putting them out there to realizing it actually something that you have to keep track of. I completely agree. And life extension is a nightmare. Oh, it's very, very challenging.
Thanks, Klaus. This is Vish from Shell Aberdeen. I got your point on this improvements needed on the condition monitoring of static pipes, and I agree with your point. Like when you say like you got those static lines, they call it as snakes on the seabed, and connecting to the wellhead jumpers, and you hardly get any of the pressure, temperature data. Real-time monitoring is really difficult, and especially when you're getting commingled fluid, and what you actually measure at the top side is it's not to the accurate these jumpers are actually seeing. So what is the strategy you've been following? Is it like you just replace these jumpers after the end of the design life, or I don't know, it's a general question. Like,
Think we are working on that. Is the question, but it's very difficult when the barrier is design. You have to verify the original design that is actually that is within the design limitations all the time. And as the Christian say, in 2005 it was decided to throw the data in on a saving campaign, which in hindsight was not a wise decision, but then hindsight is the only exact science there is. So we have the information we have, and we're trying to do it, and I know you're doing exactly the same.
Yep.
And I haven't got an answer.
Yeah. Right.
Hey, Torgrim Andersen, Kongsberg Oil and Gas. You had a slide on in-service inspection and this Caucus monitoring. And I just wonder, how do you choose up front where you're going to put on all this equipment? Which risers?
The multi-layer Kuflon risers.
Only those?
And we're seeing if we need to extend that into be applicable to all multi-layer risers. But so far we believe that the loss of plasticizer has a detrimental effect on the overall behavior, and it's less for the normal for the Gamma Flex risers, and they have operated significantly shorter time.